Deep in space, some nebulae are birthing stars at an impossible speed. This cosmic acceleration defies our most advanced scientific models, presenting a puzzle that strikes at the very core of astrophysics. By the end of our journey, you will understand the hidden forces rewriting the story of star formation. What unseen mechanisms are turbocharging these stellar nurseries, and what do they reveal about the universe's fundamental rules? How does it change your view of the cosmos to know that our maps of creation are still being drawn? This majestic process of star formation is a cosmic ballet choreographed by gravity. Picture a nebula not as a static cloud, but as a slow-motion storm of gas and dust, so vast and diffuse that for eons, nothing seems to happen. Then, almost imperceptibly, a denser knot of material begins to pull inward, drawing in more gas, building mass with the patience of a geological age. Over millions of years, this collapsing core grows hotter and denser, its internal pressure mounting until it crosses a fundamental threshold. At that critical moment, the furnace of nuclear fusion roars to life, transforming the cloud's heart into a shining new star. This is the standard model, a beautifully predictable conveyor belt where gravity does the heavy lifting at a measured, stately pace. It is a story we thought we understood completely. But what happens when we point our telescopes at certain nebulae and see this entire timeline compressed into a cosmic blink? The conveyor belt is not just speeding up, it is being fundamentally rewired, and the elegant picture we have long held is cracking under the weight of new, astonishing evidence. The Orion Nebula shatters our expectations of a quiet stellar nursery. It is a cosmic metropolis in a constant state of construction, where new suns ignite at a pace that leaves our best models struggling to keep up. This is not the slow, patient work of gravity alone. Imagine a city block where new buildings are not just going up one by one, but entire skylines are being assembled simultaneously in a frenzy of activity. That is the scene unfolding within Orion's glowing clouds. Astronomers see protoplanetary disks, the birthplaces of future planetary systems, crowded together in a dense urban sprawl. Young, brilliant stars are packed into this neighborhood, their fierce radiation and powerful stellar winds battering the surrounding gas. This intense environment is the key. It suggests that star formation here is not just a solo act of collapse, but a community project where the violent energy from one newborn star can trigger the birth of its neighbors in a chain reaction. The Orion Nebula stands as our most compelling evidence that something crucial is missing from our cosmic blueprint. If our foundational model fails to explain a place as famous and well-studied as this, what other secrets are we overlooking in the deeper darkness of space? The Tarantula Nebula takes this cosmic mystery to an entirely new scale. Far beyond our own Milky Way, in the neighboring Large Magellanic Cloud, this immense cloud of gas and dust is a stellar factory operating at a furious, almost violent pace. It forges massive stars, the kind that burn brilliantly and die young, at a rate that dwarfs anything in our local galactic neighborhood. The environment here is one of pure, unbridled energy, dominated by the most extreme stellar families in the universe. According to our established rules, this very energy should spell the end for star birth. The intense radiation and supersonic winds from these brilliant, hot stars should blast away the surrounding gas, dispersing the raw materials needed to build new suns and effectively shutting down the production line. The factory, by all rights, should silence itself, yet when we observe the tarantula, we see the impossible. New stars are igniting right in the heart of this chaos. defying the very forces that were meant to suppress them. This is the core of the paradox. How can star formation not only persist but thrive in conditions that should snuff it out? This glaring contradiction points to a fundamental flaw in our models. We are clearly missing a crucial piece of the puzzle, a hidden mechanism that allows these nebulae to harness their own intense energy and recycle it back into the birth of new stars. It forces us to question whether our understanding of how energy and matter interact in these extreme environments is fundamentally incomplete, pushing us to search for new physical principles operating in the cosmos. Even the most famous cosmic landmarks are not what they seem. The pillars of creation, those majestic towers of dust and gas immortalized by the Hubble telescope, tell a story far more complex than their serene appearance suggests. They are monuments caught in a cosmic tug-of-war. On one side, immense ultraviolet radiation from nearby, brilliant stars is relentlessly scouring their surfaces, stripping away material in a process of slow, inevitable erosion. By the conventional rules of star formation, this should be a place of death, not birth. The very energy that carves these beautiful shapes should also be blowing the stellar nurseries' raw materials into the void, shutting down any chance of new stars igniting. Yet the observations reveal a stunning contradiction. Deep within these pillars, new stars are flickering to life. The destructive force is not just a sculptor, it is a hidden midwife. This counterintuitive phenomenon is known as radiation-driven implosion. The intense pressure from the stellar radiation does not merely push gas away. In the dense, shielded hearts of these pillars, it can actually compress pockets of gas to a critical point, squeezing them until they collapse under their own weight and spark new suns into existence. Here, creation is not happening in spite of the destruction. It is being directly triggered by it. This forces us to see these cosmic forges in a new light, where the agents of chaos and the architects of order are one and the same, forever entwined in the delicate dance of stellar birth. This chaotic churning within the nebula is more than just background noise. It is the engine of acceleration. To understand it, think of a perfectly still pond. A leaf falling on its surface takes a long, slow time to sink through the calm water. Now, replace that pond with a churning rapid, where violent, swirling currents constantly force objects together and drag them downward. In this turbulent environment, the leaf would be pulled under in a fraction of the time. This is the fundamental difference inside these prolific stellar nurseries. The gas is not calm. It is a supersonic maelstrom, a form of internal weather with chaotic winds moving faster than sound itself. These supersonic motions do not just stir the cloud. They act like immense, invisible pistons, slamming into pockets of gas and creating dense shock fronts and long, thin filaments. This process compresses the material not over millions of years, but in a cosmic instant, violently bypassing the slow, stately collapse of our traditional models. A protostar that should take eons to coalesce can instead be squeezed into existence with breathtaking speed. This internal turbulence provides a powerful answer to one part of our puzzle, revealing how the raw materials for stars can be assembled on a drastically shortened timeline. Yet a crucial question remains. What is the source of this incredible turbulence in the first place? What cosmic forces are stirring the pot with such ferocity? There is another, invisible architecture woven through these clouds, a hidden framework that guides their every move. Magnetic fields flow through the emptiness of interstellar space, acting like a cosmic skeleton that supports vast clouds of gas. For a long time, we saw these fields as a gentle, restraining force, a web that holds the cloud up against the relentless pull of its own gravity. But the reality is far more dynamic. In the intense environments of these fast-forming nebulae, this magnetic scaffolding can become twisted and chaotic. When these field lines become tangled, their supportive strength can weaken, creating fragile points in the cloud structure. Suddenly, the balance of power shifts and gravity finds 1,000 new ways to win. This is where a subtle but critical process called ambipolar diffusion comes into play. Think of the cloud as a crowd of people, some holding powerful magnets and others not. The people with magnets are locked in place by the invisible field, resisting any movement. But the neutral people, the ones without magnets, can slowly slip through the crowd, weaving past those who are stuck. Over immense timescales, this slippage allows neutral gas to drift past the ionized particles anchored to the magnetic field lines. This process drains support from key regions, enabling gravity to focus its power with startling efficiency. What was once a broad, slow collapse becomes a rapid, targeted implosion in a specific pocket of the cloud, dramatically accelerating the entire birth of a star. This hidden magnetic choreography, shifting from support to surrender, is a vital key to understanding how the universe can sometimes fast-forward its own creation. Sometimes the most powerful creative force in the cosmos is a cataclysm. Far from the turbulent heart of a nebula, a massive star reaches the end of its life and explodes in a supernova, unleashing a titanic wave of energy. This shockwave travels for light years across the void, a near-invisible ripple in the fabric of space. When it finally encounters a quiet, stable cloud of gas, the effect is anything but gentle. The serene cloud is struck by a cosmic tsunami. This immense pressure front slams into the gas, crushing it in a violent, instantaneous squeeze that gravity alone could never muster. Within that chaotic compression, dozens of dense knots can form all at once. Each one becomes the seed for a new star, igniting not in a slow sequence, but in a brilliant, simultaneous flash. This is triggered star formation, and it forges entire families of stars together in a single, explosive event. Our standard models, which focus on a cloud collapsing in peaceful isolation, are completely blindsided by this external chaos. It reveals that the universe has a shortcut for building stars, one where death in one corner of space gives a sudden, violent birth to life in another. This interconnectedness forces us to see the galaxy not as a collection of separate events, but as a single, dynamic web, where a single shockwave can rewrite the fate of an entire cosmic neighborhood. Within the most crowded stellar nurseries, a different kind of gravity takes over. Isolated clouds rely on their own mass to collapse, but in the dense core of a massive cluster, the rules change completely. Here, the combined gravitational pull of thousands of protostars, gas clumps, and young suns creates an immense collective well of attraction. Picture a ball pit where a single ball sinks slowly into a shallow dip. Now imagine dozens of people standing together in the center, their combined weight creating a deep, steep funnel. Every nearby ball rolls swiftly down into that concentrated depression, piling on rapidly. This is the cosmic reality inside these dense hubs. The collective gravity acts as a powerful focusing lens, channeling vast rivers of gas inward from all directions. This creates a runaway scenario where the rich truly get richer. The most massive protostars at the center pull in the most fuel, growing even larger and increasing their gravitational reach, which in turn pulls in even more gas. It is a self-feeding cycle of astonishing speed and efficiency. While a lone protostar in a quiet region might take millions of years to gather its mass, one at the heart of this gravitational maelstrom can achieve the same feat in a far shorter time, dramatically accelerating the entire cluster's star formation rate. This reveals a universe where community and proximity are not just details, but fundamental drivers of cosmic creation itself. Our cosmic census of these stellar nurseries might be missing a crucial part of the population. We map nebulae by the light they emit or the shadows they cast, but what if a substantial portion of their material is simply invisible to our current eyes in the sky? This is the compelling mystery of dark molecular gas. Vast reservoirs of cold, dense hydrogen molecules could be woven throughout these clouds, completely undetectable by the radio telescopes we typically use to probe such regions. This unseen mass would be a game changer. Think of a cloud's gravity as its appetite for collapse. If we have only been measuring the visible appetizer, while a much larger, hidden main course sits right in front of us, then our entire prediction of how quickly that cloud should feast upon itself is completely wrong. A nebula secretly bulging with this dark gas would possess a far stronger gravitational pull, crushing its own material into new stars at a pace that our incomplete models would never anticipate. The invisible becomes the essential, suggesting that the true architects of these accelerated stellar factories are hiding in plain sight, in the form of mass we have not yet learned to see. But the story does not end with the forces we can see or even the mass we cannot. Another invisible player is at work, streaming through the void at nearly the speed of light. Cosmic rays, atomic fragments accelerated by distant supernovae and black holes, constantly bombard these stellar nurseries. They are the ultimate penetrators, slicing deep into the hearts of molecular clouds that visible light cannot breach. When one of these high-energy bullets strikes a gas molecule, it does something profound. It strips away an electron, ionizing the atom and creating a faint, pervasive electrical charge throughout the cloud. This subtle spark of energy might seem insignificant, but it rewires the cloud's internal circuitry. Remember the magnetic scaffolding that supports the gas. Ionized particles become locked to these magnetic field lines, providing crucial support against gravity's pull. But with more ionization from cosmic rays, the rules of the game shift. The increased number of charged particles changes how effectively the neutral gas can slip past the magnetic barriers in the process of ambipolar diffusion. In a region flooded with cosmic rays, this resistance to collapse can be dramatically lowered. It is as if the crowd we imagined earlier is suddenly filled with more people holding magnets, but the magnets have become weaker, or the crowd itself has become more slippery. The neutral gas finds it easier to flow, to drain away from the magnetic support structure and pool into dense, collapsing knots. The result is a gravitational collapse that proceeds not with a slow, stately grace, but with a swift and decisive rush. A nebula bathed in a higher flux of these cosmic particles could see its star formation rate surge, as if an invisible hand has loosened the very brakes on creation itself. This reveals a universe where the most violent events in the cosmos, occurring light years away, can fine-tune the birth of new suns in a distant cloud, connecting the entire galaxy in a delicate and invisible web of cause and effect. The very chemistry of a nebula holds a powerful key to its creative speed. Every cloud of gas and dust has its own unique fingerprint, a chemical identity defined by its metallicity. This term does not just refer to metals like iron, but to the total abundance of every element heavier than the primordial hydrogen and helium forged in the Big Bang. These heavier atoms, along with the molecules they form like carbon monoxide, act as the cloud's internal air conditioning system. They are incredibly efficient at radiating heat away into the cold of space. Think of a hot engine. Without a cooling system, it would quickly overheat and seize up. But with a radiator, the heat is carried away, allowing the engine to run smoothly and efficiently. In a nebula, this cooling process is vital. As a pocket of gas collapses, it heats up, If that heat cannot escape, the rising internal pressure pushes back against gravity's crush, putting the brakes on the entire process. But when heavy elements are present, they siphon away that heat, allowing the gas to continue its inward fall unimpeded. This should mean that metal-rich clouds, with their superior cooling, form stars much faster. And they often do, but then we look out to the dwarf galaxies and the distant early universe, to nebulae that are pristine, almost devoid of these heavy elements. According to our rules, these low metallicity environments should be cosmic deserts for star birth, their gas too hot and puffed up to collapse effectively. Yet, bafflingly, some of them are stellar factories. They are forging new suns at a rate that defies their own chemical limitations. This paradox forces a profound question. If the standard cooling system is broken or missing in these clouds, what other, more primal mechanism is taking over? How is the universe finding a way to bypass its own established rules, chilling these clouds through some hidden process we have yet to comprehend? The answer may lie not in the chemistry we can easily see, but in the fundamental physics of hydrogen itself, or in the sheer, overwhelming force of gravity in environments so different from our own galactic neighborhood. Yet, even as a star gathers its material, it begins to shape its own destiny and the fate of its neighbors. Deep within a collapsing cloud, a newborn protostar does not simply draw matter inward in a placid flow. It spins, and as it spins, it launches two searingly hot, narrow jets of gas from its poles, shooting outward at nearly the speed of sound. These protostellar jets are the star's first breath, a powerful exhalation that carries a critical property away from the infant sun: angular momentum. Think of an ice skater pulling her arms in to spin faster. Now imagine if she could throw away her own momentum, allowing her to pull her arms in even tighter and faster without whirling out of control. That is precisely what these outflows accomplish. By rocketing spinning material away into space, they remove the rotational energy that would otherwise fling the infalling gas away, permitting vastly more material to spiral down and feed the growing star. Our models account for this, but they may profoundly underestimate its true power. In the crowded, dense environment of a hyperactive nebula, these jets are not just gentle releases of pressure. They act like cosmic blowtorches, carving precise, blistering cavities through the surrounding cloud. This focused fury does more than just clear a path. It slams into the neighboring gas and dust with immense force. The shockwave from a single jet can crush a quiet pocket of gas into a new dense core, squeezing it until it collapses and ignites a second star. That new star may then fire up its own jets, triggering a third and a fourth. This creates a cascade of stellar birth, a chain reaction of creation where one star's violent birth directly midwifes the next. Our simulations struggle to capture this delicate, explosive domino effect. They can model a single star's formation, but the intricate feedback loop of an entire stellar neighborhood, where outflows are not just byproducts but active architects, remains a frontier of cosmic understanding. The true architecture of a nebula is not a formless cloud, but a cosmic spider web. Recent observations from powerful telescopes like Herschel have peeled back the veil, revealing that these stellar nurseries are structured around a complex skeleton of interstellar filaments. These are not mere wisps of gas. They are long, dense, and incredibly thin tendrils of cold molecular gas, stretching for light years across the void. They form the fundamental bones upon which stars are built, a hidden framework that orchestrates the entire process of creation. Within this web, gravity finds a superhighway. Instead of pulling material inward from a vast, three-dimensional volume, the geometry of a filament naturally funnels gas along its length, channeling it like water rushing through a deep ravine. This focused flow gathers immense amounts of material into dense, gravitationally unstable nodes where the filaments intersect. These knots become the direct seeds for new star systems, and the entire assembly line is dramatically streamlined. The critical question then becomes one of timing. How quickly does this cosmic web form and evolve? If these filaments are pre-existing structures woven by ancient galactic forces, or if their own formation occurs in a sudden, rapid burst, then the entire star formation timeline we have long relied on is fundamentally wrong. The slow, chaotic collapse of a cloud is replaced by a swift, organized delivery system. Material does not need to wander for eons. It is efficiently shunted along these cosmic rails directly into the furnaces of newborn suns. This offers a profound structural explanation for the baffling speeds we observe. The universe is not just stirring the pot faster, it has built a better, more efficient pipeline for creation itself. Perhaps the greatest obstacle we face is not in our predictions but in our starting point. Every simulation of star formation begins with a set of assumptions about the initial state of a gas cloud. We define its density, its temperature, the subtle internal motions of its dust and gas, and the strength of its magnetic scaffolding. These are the foundational ingredients for any virtual stellar nursery. The challenge is that we can never know these initial conditions with perfect precision. The slightest, most imperceptible variation in any one of these factors can steer the virtual cloud toward a completely different future. A cloud that begins its life just a little bit denser, or with a fraction more internal turbulence, might collapse into stars in a fraction of the time. This is known as the initial conditions problem, and it creates a profound uncertainty at the very heart of our models. It raises a startling possibility. What if the nebulae we observe forming stars at breakneck speeds are not breaking the rules at all? What if they are simply the cosmic outliers, the naturally gifted prodigies that started life with every possible advantage? These could be clouds that were born supercritical, meaning their gravity was overwhelmingly powerful compared to the magnetic fields that usually provide support. Or they might have been seeded from the beginning with a level of supersonic turbulence we rarely account for in our standard simulations. If this is true, then our entire perspective might be skewed. We could be comparing our general predictions to a carefully selected sample of the most extreme and unusual stellar factories in the universe. Our models might be far more accurate for the quiet, typical nebulae, while we stand baffled by the spectacular exceptions, the cosmic overachievers that were destined for greatness from their very first moment. These computational limitations force a difficult trade-off. A simulation can either capture the grand sweep of a nebula spanning hundreds of light years, or it can zoom in to model the intricate physics within a single, collapsing protostellar core. It is nearly impossible to do both at once with perfect fidelity. To make the problem manageable, our models must simplify reality, smoothing over the chaotic, small-scale details that might hold the key to the mystery. Think of trying to predict the exact path of a single leaf in a hurricane. You could model the massive storm system as a whole, or you could simulate the complex air currents around that one leaf, but combining both into a single, perfect forecast is beyond our current reach. In the cosmos, this means the vital, fine-grained interactions are often lost. The models might average out the fierce, supersonic turbulence that acts like 1,000 invisible pistons, compressing gas in an instant. They may gloss over the sudden, explosive snap of magnetic field lines, a process called reconnection, that can release immense energy and violently stir a local pocket of gas. These are not mere details. They could be the very engines of acceleration, the hidden mechanisms that our simulations, by their necessary design, are quietly erasing. We are trying to read the universe's most complex blueprint, but we are missing the fine print that explains how the building truly gets done so fast. Our own eyes on the sky might be unintentionally deceiving us. Every telescope, no matter how powerful, has its limits. When we gaze into a vibrant nebula, we are mapping its stellar population based on what we can detect. But what if we are only seeing the brightest, most obvious newborns? We could be completely missing a vast, hidden population of faint, low-mass stars, the dim red dwarfs that burn for trillions of years. More crucially, our view might not penetrate deep enough to spot the youngest protostars, those still swaddled in thick, opaque cocoons of dust. They are there, gathering mass, but completely invisible to our most sensitive instruments. This creates a profound observational bias. If our census is missing these countless faint and hidden stars, then the true number of stars being born is far greater than our tallies suggest. The consequence is startling. The formation rate is not just fast, it is astronomically faster than we ever measured. We have been judging the speed of a cosmic race while only clocking the fastest runners, completely unaware of the thousands of others still hidden in the starting blocks. Compounding this, our view is a snapshot, a single frame in a movie that spans millions of years. We see a nebula blazing with youthful stars and assume it has been producing them at this furious pace for eons. But what if we are witnessing a short, violent burst of creation, a brief fireworks display in the long, quiet night of the cloud's existence? If that is the case, then we are not looking at a sustained high rate, but a temporary spike, and our models are not just wrong about the speed, but about the very rhythm of stellar birth itself. The universe may not be breaking its own rules, it may simply be performing a dance we have only just begun to see. This fundamental question of how much gas a cloud actually uses brings us to a critical cosmic metric known as star formation efficiency. It is a beautifully simple yet profound concept. Think of a baker making a loaf of bread. The efficiency is the amount of flour that actually ends up in the final baked loaf versus the amount that gets scattered on the counter, lost to the air, or left stuck in the bag. In the cosmos, this is the fraction of a nebula's vast reservoir of gas that successfully collapses all the way into shining stars. Our modern models have long predicted a certain, modest level of efficiency for a typical stellar nursery, a gentle, sustainable pace of conversion. But when we look at the real universe at places like the Orion or Tarantula Nebulae, we find a glaring discrepancy. The observed efficiency is dramatically higher. These cosmic bakeries are not leaving much flour on the counter at all. They are managing to pack a far greater percentage of their raw material into the final stellar loaves. How is this possible when the intense feedback from young stars should be blowing the kitchen apart? The answer may lie in the sheer, overwhelming density of these exceptional clouds. Imagine trying to shout down a raging river. Your voice, no matter how loud, is simply swallowed by the thunder of the water and the immense pressure of its flow. In these ultra-dense nebulae, the furious winds and searing radiation from newborn stars may meet a similar fate. They are trying to push against an ocean of gas, a medium so thick and heavy that their power is absorbed and muted before it can effectively halt the inward rush of material. Accretion, the steady flow of gas onto a growing protostar, continues unabated. The feedback that should shut down the assembly line instead becomes a mere whisper, lost in the roar of gravitational collapse. This allows these prodigious nebulae to achieve a staggering feat, converting a much larger portion of their bulk into stars and creating the spectacularly high formation rates that leave our models, calibrated for quieter environments, completely baffled. The true answer likely lies not in one single cosmic rule-breaker, but in a powerful, orchestrated chorus of them. No single mechanism we have explored acts alone in these stellar powerhouses. Instead, they combine and amplify one another in a symphony of creation, where the final result is far greater than any individual part. Imagine a nebula born with a fortunate head start, its initial conditions already tilted toward rapid collapse. Then, a distant supernova sends a shockwave rippling through its depths, injecting a massive dose of supersonic turbulence. This chaos churns the cloud, but it is the nebula's own intricate magnetic skeleton that guides that chaos, its fields twisting and snapping to focus the energy into precise, collapsing knots. Within this maelstrom, the first protostars ignite, and their furious jets and radiation, rather than just causing disruption, now interact with the pre-stirred environment. They compress already dense regions, triggering second and third generations of stars in a cascading chain reaction. This is a nonlinear system, a feedback loop of cosmic proportions where gravity, turbulence, magnetism, and stellar feedback constantly reshape one another. A small change in one factor does not create a small, predictable change in the outcome. It can tip the entire system into a new state of hyper-efficiency, an emergent behavior that our simpler models, which study each force in isolation, are completely blind to. We have been searching for a single key to unlock this mystery, but the universe is showing us that we need the entire keyring. The echoes of creation itself whisper to us from across cosmic time. By peering back to the dawn of the universe, we find stellar nurseries operating under a radically different set of rules. These primordial nebulae, observed at immense distances as faint, redshifted smudges of light, were composed of a purer, more fundamental recipe. They were vast clouds of pristine hydrogen and helium, utterly devoid of the heavy elements that act as cosmic coolants in modern clouds. According to everything we understand about star formation, this should have made them inefficient and slow. Without those heavier elements to radiate heat away, the gas should have remained too hot and pressurized to collapse easily. Yet the evidence tells a different story entirely. These ancient clouds forged the very first stars at a breathtaking pace, assembling immense, brilliant clusters that lit up the early darkness. How was this possible? The physics in these environments must have been extreme, operating on a scale of pure, unadulterated power. The young universe was a more compact and violent place, rippling with the aftermath of its own birth. This likely seeded the gas with levels of supersonic turbulence far beyond what we see locally. This foundational chaos, combined with the sheer, overwhelming force of gravity in a denser cosmos, could have driven a rapid and decisive collapse even without the sophisticated cooling mechanisms of later eras. The first stars were not built with finesse, but with raw, gravitational might. This suggests that the fundamental principle of fast-tracked star formation, the ability of immense turbulence and gravity to override other limitations, is not a new invention. It is the universe's original, default setting for building stars, a primal blueprint that still lies dormant, waiting to be reawakened in the most extreme environments of the modern cosmos. A new era of cosmic observation has begun, one that peers directly into the heart of creation. The James Webb Space Telescope, with its revolutionary infrared vision, is pulling back the dusty veil that has long hidden the earliest moments of star birth. Where Hubble showed us the majestic, sculpted surfaces of nebulae, Webb sees right through them, revealing the bustling activity within. Its stunning images of the Orion Nebula are not just pictures, they are detailed blueprints of a stellar factory in motion. We can now see countless protostars, each swaddled in its own dense cocoon of gas and dust, with swirling disks of material that will one day become planets. This is the hidden population our models could only guess at, now brought into sharp, brilliant focus. For the first time, we are not theorizing in the dark. We can directly measure the supersonic turbulence churning the gas, trace the intricate skeletons of interstellar filaments down to their finest threads, and watch in real time as the fierce jets from newborn stars slam into their surroundings. This torrent of new data acts as the ultimate judge for our competing theories. It will confirm which mechanisms truly drive the acceleration, revealing whether magnetic fields, turbulent compression, or cascading feedback holds the primary key. Some of our most cherished ideas will be validated, while others, we must be prepared to see shattered against the rocks of hard evidence. The mystery of the accelerated nebulae is no longer a distant puzzle, but a question on the verge of being answered as we finally watch the universe's greatest show from a front-row seat. There is another, more ghostly architect that might be sketching the blueprints for these stellar factories. We must consider the role of dark matter, the universe's most pervasive and enigmatic substance. This invisible material does not emit or absorb light, making it impossible to see with any telescope, yet its gravitational influence is the cosmic glue that holds galaxies together. In a typical nebula like Orion, the concentration of regular or baryonic matter is so high that the subtle, diffuse gravity of dark matter is negligible. It is a whisper drowned out by a shout, but venture into the sparse outskirts of dwarf galaxies or travel back to the primordial universe, and the balance of power shifts dramatically. In these realms, the density of normal gas and dust is far lower. Here, the vast, overarching halo of dark matter surrounding a galaxy can become the dominant gravitational force. Its steady, pervasive pull could act as a massive, invisible template, gently guiding and concentrating the sparse baryonic matter, helping it coalesce into clouds much faster than it could on its own. This remains a speculative frontier, a hypothesis that challenges the very boundaries of astrophysics. Yet its profound implication is that we may be missing a fundamental ingredient in our cosmic recipes. The most extreme cases of rapid star birth, especially in the ancient or most minimalist galaxies, might not be driven by the matter we see, but by a silent partnership with the matter we cannot. It suggests that the full story of creation requires us to listen for the whispers of the dark. A star's death can write the opening chapter for a new generation's life. The most colossal stars burn with a ferocious intensity, but their brilliance is fleeting, lasting only a few million years before they exhaust their nuclear fuel. This brief, spectacular life is not a quiet one. From the moment of their ignition, these stellar giants reshape their entire neighborhood. Their immense ultraviolet radiation acts like a cosmic blowtorch, heating the surrounding gas and driving powerful stellar winds that flow outward at millions of kilometers per hour. This relentless energy carves out immense cavities within the nebula, sculpting vast, hollow bubbles that can span hundreds of light years. On the surface of these expanding shells, something remarkable happens. The shockwave from the bubble's growth slams into the cooler, denser gas surrounding the void, crushing it in a sudden, violent squeeze. This compression is the trigger. It forces pockets of gas to reach a critical density, collapsing them into new stars in a process that is far faster than the nebula's background rate. This is sequential star formation, a cosmic chain reaction where one stellar generation directly begets the next. The first wave of massive stars dies in supernova explosions, whose shockwaves then trigger a second wave on the bubble's new, larger surface. That second generation then lives and dies, potentially triggering a third. From our distant vantage point, observing this entire complex over a short cosmic timescale, we do not see a slow, steady trickle of stellar births. Instead, we witness what looks like a single, spectacularly high formation rate. The nebula appears to be in a state of constant, frenzied production. Our time-averaged models, which smooth out these violent, punctuated bursts of activity over millions of years, can completely miss this dynamic reality. They are designed to understand the slow, steady rhythm of a cosmic heartbeat, but in these regions the heart is pounding, creating a rapid-fire staccato of creation that our simulations are only beginning to learn how to hear. The silent chemistry of a collapsing cloud can accelerate its own demise. Deep within these stellar nurseries, the gas is not a simple, inert substance. It is a dynamic chemical laboratory where atoms constantly meet, bond, and transform. The most crucial reaction is the quiet formation of molecular hydrogen. When two lone hydrogen atoms meet and link on the surface of a microscopic dust grain, they create a molecule of H2. This seemingly simple handshake is a cosmic game-changer. Molecular hydrogen is far more efficient at radiating away heat than its atomic form. It is the cloud's primary cooling system, allowing the warmth of gravitational collapse to bleed out into space. But the chemistry does not stop there. Heavier atoms like carbon and oxygen also join the dance, bonding to form carbon monoxide. This molecule is an even more powerful coolant, a super-efficient radiator that chills the gas to dramatically low temperatures. As the cloud grows colder, a strange phase change occurs. Atoms and molecules begin to freeze directly onto the surfaces of dust grains, creating icy mantles that coat the tiny particles like frost on a windowpane. This process of depletion removes even more warm material from the gaseous state, further enhancing the cloud's ability to cool and contract. Imagine two identical clouds beginning their collapse. One is chemically primitive, it's gas-hot and slow to cool. The other is a chemical wonderland, rich with efficient molecular coolants and icy dust grains that rapidly siphon away thermal energy. The second cloud would not just cool faster, its entire internal structure would change. The cold, dense gas becomes fragile, susceptible to splintering into countless self-gravitating fragments under the slightest pressure. This is the chemical head start. A nebula blessed with these unique pathways does not follow the slow, stately timeline of our standard models. Its journey from a diffuse, quiet cloud to a crowded metropolis of dense, star-forming cores is dramatically shortened, as if the universe has discovered a chemical shortcut to building stars. The intricate dance of a single collapsing star is complex enough, but the universe often prefers to build in pairs and groups. A surprising number of stars are not born alone. They emerge from the cosmic cradle as binary systems, locked in a gravitational embrace, or even as sprawling multiple families of 3, 4, or more suns. This inherent sociability of stars introduces a layer of dynamic chaos that our single star formation models are only beginning to grasp. The process of building one star is a delicate balance between gravity pulling in and pressure pushing out. Now picture that same cloud trying to orchestrate the simultaneous collapse of 2 or 3 distinct cores, all while they whip around one another in a frantic orbital dance. The gravitational dynamics become a tangled web of pulls and tugs, a far cry from the orderly, inward-focused collapse we typically simulate. This gravitational interplay between the infant protostars does not just stir the pot. It can create a powerful slingshot effect. As the protostars swing past one another in their orbits, their mutual gravity can efficiently fling streams of gas and dust inward, channeling material directly into their growing cores. It is a gravitational feeding frenzy where the complex motions of the group draw in fuel more efficiently than any single star could manage on its own. The accretion process, the steady accumulation of mass, is supercharged for all involved. This means a nebula with a natural predisposition to fragment into many multiple systems possesses a hidden engine for acceleration. Its overall star formation rate could be dramatically boosted, not in spite of the chaos, but because of it. Our single-star models, focused on a solitary and relatively placid birth, would look at such a nebula and see only an impossible rate of production. They are blind to the collaborative rush of stellar siblings, all helping each other grow up far faster than they ever could alone. The galaxy itself acts as the grandest stage for stellar birth. A nebula is not an island, but a neighborhood within the sprawling city of its home galaxy, and its cosmic address dictates everything. Whether a cloud resides in the serene suburbs between spiral arms, the dense, bustling core, or is flung out into a lonely tidal stream, it experiences a completely different set of galactic forces. The most dramatic shifts occur when a nebula drifts into one of a galaxy's majestic spiral arms. This passage is not a gentle transition. It is like a ship entering a powerful oceanic current, where the combined gravitational pull of billions of stars and vast, unseen dark matter creates a zone of immense pressure. This galactic scale squeeze compresses the gas cloud on a monumental level, not from the inside out, but from the outside in. The trigger for collapse is no longer a local phenomenon. It is a command from the galaxy itself, initiating star formation simultaneously across vast stretches of the cloud. This external driver can force a quiet, stable nebula into a sudden, prolific burst of creation, explaining why we might observe a brief, intense flurry of stellar births that our isolated cloud models could never predict. The very rhythm of a galaxy, its slow, stately rotation, and the passage of its density waves can set the tempo for star formation, turning the lights on in stellar nurseries not at random, but in a coordinated galactic pulse. This reveals that to understand the life of a single nebula, we must first listen to the heartbeat of its entire galaxy. Our models have long pictured star birth as a solitary affair, a single cloud turning inward on itself in quiet isolation. But the universe builds on a grander, more connected scale. The collapse of a massive nebula is not a collection of separate events. It is a global, coordinated phenomenon where countless pockets of gas and dust all begin to fall, not just toward their own local centers, but toward the cloud's overarching center of mass. This is the difference between an isolated collapse and a convergent one. Imagine a crowd of people scattered across a vast, sinking landscape. If each person simply dug their own hole, the process would be slow and individual. But if the entire ground tilted toward one deep central basin, everyone would slide inward together, converging into a single, dense crowd in a fraction of the time. This is the hierarchical reality inside a nebula like the Tarantula. The entire structure is collapsing from the top down, with smaller regions cascading into larger ones, all funneling material toward a common gravitational well. This synchronized motion creates a powerful rush of infalling gas, a cosmic river that feeds not one star, but an entire cluster simultaneously. The result is not a slow, sporadic sparking of individual suns, but the rapid, brilliant ignition of a whole stellar metropolis at once. This top-down blueprint could be the master plan we have been missing, the natural cosmic architecture that explains how these immense factories assemble their stellar populations with such breathtaking and seemingly impossible speed. Perhaps we have been measuring the wrong thing entirely. Our standard metric for a nebula's productivity is its star formation rate, usually expressed in solar masses per year. This number tells us how much raw material is being converted into stellar fuel over time. But this simple measurement hides a critical variable, the very blueprint for the stars being built. This blueprint is known as the initial mass function. It is the cosmic rulebook that dictates how many small, dim red dwarfs will be born for every brilliant, heavyweight stellar giant. In a typical, quiet region of our galaxy, this rulebook is remarkably consistent. For every single massive star that forms, hundreds of smaller, lighter stars are also created. It is a predictable distribution, a cosmic census we thought was universal. But what if inside these accelerated nebulae that rulebook is being rewritten? The fundamental recipe for a stellar population could be shifting. Imagine two identical bakeries using the same amount of flour. One follows a standard recipe, producing a large number of small rolls and a few large loaves. The other bakery, however, has altered its process. It uses its flour to create only a handful of small rolls, but an astonishing number of massive, heavy loaves. Even if both bakeries work at the same speed, the second one would appear far more productive if you are only measuring the total weight of bread produced per hour. This is the tantalizing possibility within nebulae like the Tarantula. Their incredible formation rate, measured in solar masses per year, might not be solely due to a faster assembly line. It could be because their assembly line is preferentially crafting heavier products. If these environments are skewed toward forming a greater proportion of high-mass stars, then the sheer weight of new stars would make the entire process seem radically accelerated. The underlying physics driving this mass bias could be the real key to the mystery. Why would a nebula favor building giants? The answer may lie in the frantic pace of accretion itself. In a supremely dense and turbulent environment, the flow of gas onto a growing protostar is not a gentle trickle. It is a raging river. High-mass stars are not just larger versions of their smaller cousins, they form differently. They are gluttons capable of pulling in vast amounts of material at a ferocious rate, growing to immense sizes in a relatively short time. In a calm cloud, this rapid accretion is rare. But in a nebula already churning with supersonic turbulence and powerful gravitational focusing, the conditions are perfect for creating these stellar behemoths. The dense, chaotic gas provides a nearly unlimited food supply, and the complex dynamics efficiently channel that food toward the most massive seeds. This creates a gravitational aristocracy where the rich get richer at an astounding pace. The nebula's entire stellar census becomes top-heavy, filled with more brilliant, short-lived giants than our standard models would ever predict. So when we point our telescopes at these regions and calculate their output, we are not just seeing a faster version of the same process. We are witnessing a fundamentally different kind of creation, one that builds the cosmos with a heavier hand. This runaway collapse echoes one of the most powerful ideas in all of cosmology. We know the entire universe underwent a period of exponential expansion in its first moments, a fleeting instant of cosmic inflation that set the stage for everything to come. Could a similar, though not identical, process of runaway acceleration be happening on a much smaller scale inside these stellar powerhouses? Some theorists are exploring this very possibility. They propose that under a perfect storm of conditions, a pocket of a nebula could experience its own version of a hyper-collapse. Imagine a house of cards falling in slow motion, one card tipping the next in a predictable chain. Now imagine that same structure wired with a carefully placed domino that, when tapped, causes the entire edifice to implode in a single, synchronized flash. This is the kind of paradigm shift being considered. The trigger is theorized to be a unique and unstable configuration of magnetic fields and supersonic turbulence. If the magnetic scaffolding that normally supports the gas becomes twisted and tangled in just the right way, its supportive strength could catastrophically fail all at once. This sudden, coordinated loss of support would release the brakes on gravity simultaneously across an entire region. Instead of a slow, stately fall, the gas would experience a violent, exponential rush inward, collapsing a vast volume of material into a dense stellar seed in a tiny fraction of the usual millions of years. This remains a highly speculative frontier, a thought experiment that pushes our understanding of plasma physics to its limits. Yet its very consideration reveals the depth of our search for answers. When the standard rules cannot account for the cosmic evidence, we are forced to contemplate the universe's hidden blueprints, the ones that allow it to build stars not just quickly, but in a breathtaking, instantaneous flash. The very winds that should tear a nebula apart can also become its most powerful architects. When a massive star ignites, it floods its surroundings with a torrent of ultraviolet radiation, a force so intense it strips electrons from atoms, creating a vast, shimmering sphere of superheated, ionized gas known as an HII region. This brilliant bubble expands relentlessly, its immense internal pressure pushing outward against the cooler, neutral gas of the surrounding cloud. This interaction is a cosmic battle between order and chaos. The expanding frontier of the HII region acts like a colossal snowplow, gathering the interstellar material ahead of it and crushing it into an incredibly dense, cold shell. In many cases, this process does indeed spell the end for the nursery, as the gas is blown away into the void, but the universe thrives on exceptions. When the surrounding cloud is especially massive and dense, something remarkable occurs. The shock of compression does not destroy the cloud, it sculpts it. The immense pressure forces the gas in the shell to fragment, collapsing these new, dense pockets into a fresh wave of protostars. This is a stellar chain reaction, a positive feedback loop where the first generation of stars does not just live and die, it actively midwives the next. The entire nebula can experience a punctuated, violent burst of creation, a brilliant fireworks display of stellar birth that is completely out of sync with the slow, steady rhythm our models predict. We are not looking at a system in peaceful equilibrium, but at a cosmic engine where one explosion of light directly fuels the next. Yet our cosmic census might be missing an entire class of citizen. Brown dwarfs are the elusive, shadowy figures of the stellar world, often called failed stars. They begin their lives just like true stars, collapsing from the same clouds of gas and dust. But they never quite make it across the finish line. They are born with too little mass, less than about 7% of our suns, to ever ignite the sustained nuclear fusion that defines a true star. Instead, they glow faintly with the residual heat of their formation, slowly cooling into obscurity over billions of years. These dim objects are incredibly difficult to detect, especially when they are swaddled in the dusty cocoons of their birth nebula. If certain prolific nebulae are secretly manufacturing a vast, unseen population of these brown dwarfs alongside the brilliant stars we can see, then our entire understanding of their productivity is flawed. The total number of objects being forged would be far higher than our current measurements suggest. While an individual brown dwarf is lightweight, their collective existence points to something profound about the nebula itself. It reveals a cloud with an astonishing talent for fragmentation. The process of breaking a large cloud into smaller, self-gravitating clumps is operating at an extreme level of efficiency. Our models, calibrated for the creation of sun-like stars, may be completely blind to this fine-grained shattering of the cosmic raw materials. A nebula teeming with brown dwarfs is not just a star factory, it is a master sculptor capable of carving its gas into a breathtaking spectrum of objects, from brilliant giants to countless faint embers. This unseen population forces us to ask whether the true measure of a nebula's creative power is not just the weight of the stars it builds, but the sheer number of new worlds it brings into being. These persistent discrepancies are not a failure of our models, but a sign of their inevitable evolution. Science does not progress in a straight line. It moves in great leaps propelled by the very contradictions that first seem to undermine it. We stand at such a precipice today, on the verge of a fundamental rewriting of the story of stellar birth. Our current understanding, with its elegant but simplified equations, is the modern equivalent of Ptolemy's complex circles trying to chart the planets. It works until it doesn't, and when it fails, it paves the way for a Kepler, a Newton, an Einstein to reveal a deeper, more beautiful truth. The next great theory of star formation will not simply add another variable to our existing calculations. It will be a complete paradigm shift, a new way of seeing the cosmos. This framework will abandon the idea of a single, universal recipe. It will instead recognize a vast family of processes, a cosmic spectrum of creation. On one end lie the quiet, slow nebulae that our current models describe quite well. On the other are the extreme, fast-track powerhouses that have captivated our curiosity. Both are valid, both are real. The new theory will be a symphony, not a solo. It will seamlessly integrate the chaotic dance of supersonic turbulence with the invisible architecture of magnetic fields. It will weave in the silent, chilling chemistry of molecular gas and the explosive feedback from newborn stars. Most importantly, it will treat these forces not as separate actors, but as interconnected players in a non-linear, multi-scale drama. A tiny jet from a protostar can influence a region light years away. A galactic density wave can set the tempo for 1,000,000 individual collapses. We are learning that you cannot understand the leaf without knowing the hurricane, and you cannot predict the hurricane by studying only the leaf. This is the profound challenge and the breathtaking promise of what comes next. Our maps of creation are being redrawn in real time, not with a single bold stroke, but with the intricate, collaborative brushwork of a universe far more complex and wonderful than we ever dreamed. This synthesis of cosmic clues points toward a single, elegant conclusion. The universe's most prolific stellar factories are not breaking the rules. They are simply starting the race from a privileged position, perfectly primed for a rapid and decisive collapse. Imagine a vast cloud of gas that begins its existence already on the brink. Its initial density is extraordinarily high, granting gravity a powerful head start. Its interior is not calm, but churning with a specific, disorganized form of supersonic turbulence that acts like 1,000,000 chaotic pistons, compressing gas at a breathtaking pace. Crucially, the magnetic scaffolding that normally supports the cloud is either intrinsically weak or has become tangled and fragile. Its power to resist gravity catastrophically diminished. And often, this entire volatile system receives a final, decisive nudge from an external trigger, like the shock wave from a distant supernova. When these four factors converge, they create a perfect storm for star birth. Gravity no longer has to fight its way through a long, slow battle. It finds the path of least resistance cleared, the gas pre-compressed, and the supporting structures already compromised. The result is a runaway collapse, a cosmic chain reaction where the entire cloud seems to implode upon itself, converting its vast reserves into new suns with a speed that leaves our standard models in the dust. This holistic view transforms the mystery from a collection of baffling exceptions into a solvable puzzle. It reveals that to understand stellar creation at its most extreme, we must stop looking for a single rule breaker and start listening to the entire cosmic orchestra, where density, turbulence, magnetism, and external shockwaves play in a powerful, synchronized symphony. Our journey through these star-forging tempests reveals a cosmos of breathtaking dynamism, where creation is not a single rule but a spectrum of possibilities. We have seen how supersonic turbulence acts as a cosmic accelerant, violently squeezing gas into stellar seeds. We have traced the invisible lines of magnetic force, a scaffold that can both support a cloud and then catastrophically fail it. We have witnessed how the death of a star in a supernova can trigger the birth of thousands more, and how the silent chemistry of cooling molecules can fast-track a cloud's collapse. This grand puzzle is far from a failure of our science. It is a beacon illuminating the vibrant and ever-evolving nature of our understanding. The solution will not merely correct a page in an astronomy textbook. It will redefine our relationship with the universe, reminding us that the cosmos is a place of infinite nuance and surprise, forever inviting us to look deeper. We would love to hear your thoughts. Which of these cosmic mechanisms, from turbulent storms to magnetic snap, do you find most compelling? Share your perspective in the comments below.